All right, welcome everyone to our day 3 contributed session 2. It's my pleasure to announce our first speaker for today, Sanjay Mishra, who will be telling us about preservation of properties during topological equivalence of function spaces. Thanks, Sanjay.
Okay, thank you very much for giving me the opportunity to present my talk in this platform. My topic is a preservation of properties during the topological equivalence of a function space. The outline of this talk, first here I would like to discuss about the summary of this talk, the topological function space, duality properties of the topological function space, t-invariancy of the cardinal functions, and t-invariancy of some spaces. And here I would like to also discuss two unsolved problem that here I found in the literature, and how to solve this problem, that also I have idea, but not much more. Here I work on this and the references. So the study of a convergence of sequence of a function is the most important and active area of the research in theoretical mathematics that solve the problem of approximation theories, Fourier analysis, function analysis, measure theory, group theory, or ring theory of mathematical modeling, also the computer science. The topological approach is a very important and the very popular idea that solve the problem related to this fundamental concept. The primary goal of the study of function space with the topological approach is to investigate the convergency of the sequence of function over the some topological spaces. In this talk, we are going to discuss about the preservation of properties during the topological equivalence that we here call the t-equivalence of a set of real valued continuous functions under the topology of pointwise convergence. So first thing that here, which type of the topological function space that we are going to here consider. The first is that the topology of pointwise convergence on the CX. CX means here the set of continuous functions from X to R. So it is a set of real valued continuous function, and where the X is a Teknoff space. So how the topology of a pointwise convergence is defined, here you can see where xi is any arbitrary element of the X, and oi is the arbitrary open subset in the R, where the I belongs to this capital I is the index set, and the n belongs to the set of positive integer. Then the collection tau p, that is a collection of a element of the CX as a U, which hold these conditions, where the xi y is the set that is made by the element of the CX as a function that hold the fxi belongs to y. So this collection is actually called the topology of pointwise convergence on the CX. And we will denote here the notation for the CX with the topology of pointwise convergence is the CPX. So here P denote the topology of pointwise convergence. Now the local base of this topology of pointwise convergence is here defined. Here for the given f belongs to the CPX, and the xi belongs to x, and the epsilon is any positive number. Then the collection, the BF, is made by the set OFXI epsilon, where the OFXI epsilon is defined by the element G belongs to the CPX, which hold this condition. The norm of or mod of the GXI minus FXI is less than epsilon. So this is the local base of the CPX at the any element F of the CPX. So this is the mainly we are going to discuss about the topology of pointwise convergence on the structure CX. Now the problem is what? that here, how are the spaces X and Y are related to each other or far from each other in the case of CPX and CPY are homeomorphic or a linear homeomorphic or the ring isomorphic or uniformly homeomorphic. So there are so many perspectives for the similarity of two different function space, topological function space with a topology of pointwise convergence, CPX and CPY. But in this talk, I will only consider the homeomorphism between the CPX and CPY. So my problem is counter only the homeomorphism between the CPX and CPY. Now, the two important definitions that play a very important role in this talk, that is a t-equivalence space and the t-invariant property. So any two topological spaces X and Y are called a t-equivalent if their corresponding topological function space CPX and CPY are homeomorphic, and we denote this X equivalent to Y, or you can say that X t equivalent to Y. So here you can see that there are two things we have. One is a base space, that is the X and Y, and another is a richer space, CPX and CPY. So we call X and Y the base space, and their topological function space corresponding to this, that is the CPX and CPY is a base space. So when we are saying that both are related to each other, topological space X and Y, base space topology X and Y are related to each other, that means when their topological function space, richer space are homeomorphic to each other. This is the similar as a homeomorphism, but it is a little bit different because in the homeomorphism we consider only the topological space, but here we consider two things, that are topological space as a base space as well as their richer space function space. Next is a t-invariant properties. That let's see the class of Teknoff space, then the topological property P is said to be the t-invariant within the class C if it holds the condition that X and Y belongs to C, means the X and Y are the Teknoff space and X is equivalent, t equivalent to Y, and X hold the property here. This is the notation for X hold the property P, then this implies that Y is also hold the property P. And if you have any property, any such a topological property, then that topological property is called the t-invariant property. Now, my discussion is only for the class of a Teknoff space, but there is others also study that you can consider other class, but here it is only for the Teknoff space. Now we have very simple question that two discrete space are homeomorphic if and only if they have a same cardinality. That means if you have a two topological space, and how can you compare the two topological space through the cardinality? That is only possible if it is a discrete space. And if you are going to change this input condition, then it is not possible that their cardinality are same. So what is the answer by which you can say that we can replace the discrete space by a general problem? So here you can see that this theorem comes that if X and Y is a Teknoff space and X is t-equivalent to Y, then definitely the cardinality of X and Y both are same. So here you can see this what here the discrete space. This question was that the discrete space is actually give the same cardinality of the topological space, but here we consider any Teknoff any space, not only discrete space. So this result is give the better compared to our first question. So how our problem is more general compared to this. This is the first basic example or result you can say about the t-invariancy of the cardinal function. Next here, I would like to first introduce some cardinal function, and then we will see that how this cardinal function is a invariant. Weight of the space, X means the, always we consider the technographic space. So weight of the X means the minimum cardinality of the base of X, that is called the weight of X. Network weight means the minimum cardinality of the network of X. And similarly, the I weight of the X, that is denoted by the I weight of X, this is the cardinality of the kappa. There is a condensation of the X onto the space of weight less than. And the density of the X is the minimum of the cardinality of the D, where D is the nothing, it is a dense subset of. So here we can see the important result that if you consider X and Y is the technographic space and the X and Y are the t-equivalent, then here you can see that how the network weight, I weight, and the density of the both topological space are same. So you can say that the network weight or I weight or the density are invariant or T invariant when the X and Y are the equivalents. Even if you are going to consider only for the homeomorphism case, then it is not possible. So this tells us that how to compare through the function space. Next is the point finite cellularity. This is another cardinal function. So how the point finite cellularity of the X is defined, that it is denoted by the Px, and it is the supremum of the cardinality of the U, where the U is the subset of U is the family of this element of the tau star X. Tau star X means here you are not going to consider the, in these collections, it is actually the topology on X, and you are not going to consider the phi. Okay, so this is a dilated topology where the non-empty set is not considered. And the cellularity or cellular number of the any topological space X is defined as the supremum of the cardinality of the U, where this same condition are is, but the difference is only that here U is a disjoint, means all the element of the U is disjoint, will be the disjoint. Now here you can see this result tells us that how the cellularity point finite cellularity is a T invariant. But even if you are going to consider X and Y as a T invariant, it is not possible for the homeomorphism. Next is that bare space. If you are going to consider the bare space, now here one thing very important before going to discuss this theorem, that here when you are going to consider the cellularity of the X, then it is not possible under the T equivalency of X and Y. So there is some extra conditions are required, and that condition is only possible here when both X and Y are the bare space. So you can see that sometimes the T equivalency not work well as like others we discussed. So here the X and Y are the bare space and the X and Y are T equivalent, then the cellularity of the X and Y are same. So you can say that cellularity is the also T invariant, but under the certain conditions that your topological space must be bare. And another thing is that it is also possible it is when it is a pseudo compact space, because all the pseudo compact space is bare. So you can also see this. This is the particular result of the first theorem. Now the next thing, that next cardinal function is here you can see that is the caliber of X. So how the caliber of X is defined, an uncountable regular cardinal kappa is the caliber of X if for any index family U, U is defined as U alpha, where alpha is less than kappa, is a subset of the tau star X. There exists a set A of the kappa such that the cardinality of the A is always equal to K, and the intersection of all these are the non-empty. So this is the caliber of X, and the next result tells us that how the caliber of the X is a T invariant. So we have another important result that the caliber so that it is a t-equivalent property. Next is a very well known result Lindelof numbers is defined that every open cover of X as a subcover of a power k that is less than kappa, and spread that is also cardinal function. So these two cardinal functions not well, but here when we are going to consider the hereditary conditions, then it is well hold. So here when X and Y are the Teknoff space and X and Y both are the equivalent, then you can see this here. This is the Lindelof numbers, and this is the density, and here it is spread. And here the star tell us that, or H tell us that the hereditary means we are going to consider the closed set of this space X. So it is a hereditary, and a star tell us that we are going to consider a non-empty set of the tau X. So these are the also three cardinal invariant we have. Next is the tightness of the X. This is also cardinal functions, and this cardinal function also give the very important result. Same here when the X and Y are the Teknoff space and both are t-equivalent, then the tightness of the X and Y both are the same. So these are the very important cardinal functions that here we discuss. Now the next section that we are going to describe that some important spaces, how it is t invariant. So let us see the P space first. So what is the P space? The P space is a topological space in which every countable intersection of open set is open. And here P means that a pseudo discrete space, basically. So here, if we have X as a P space and X is a t-equivalent to Y, then Y is also P space. Generally, when we are going to consider in the case of homeomorphism, then it is not hold good. But in the case of t-equivalency, we have this result. Now the next result, that is sectorness or sector space. A sector space is a topological space that contains the non-empty dense in itself, or equivalently we can say that every non-empty subset A of X contains the point isolated A in the X. So here the very well behave as like other space. So if X is a sector space and both X and Y are the t-equivalent, then Y is also sector space. So all the result you can see that it is not hold for the homeomorphism, but for the t-equivalency, it is hold. Next important result is the horizon space that is recently introduced, and it is very important for discussion of other algebraic topology. That horizon space is a topological space that satisfies a certain basic selection principle that generalize the sigma compactness. Or horizon space is a space in which every sequence of open cover of U1, U2 of the space, there is a finite sets F1 contained in the U1, F2 containing U2, such that every point of space belongs to all but finitely many sets. So we have this Hausser's space, and you can see this. If we have a Xn is a Hausser's space for every n belongs to n, and X is equivalent to Y, then Yn is also Hausser's space for the every n belongs to the top natural number. So, but for the same thing here, the homeomorphism, in the case of homeomorphism, it is not hold well. Now the next two things, monolithic space, when we have any cardinal K and space K is a monolithic. If any subset A of X and the cardinal of A is less than equal to kappa, this implies that the network of this closure here, A bar denote the closure of A is less than equal to kappa. So such a space hold this condition is called the monolothic space, kappa monolothic space, and it is also T invariant properties, and you can easily see this, that if X is a monolothic space and both are equivalent, T equivalent, then the Y is also. Similarly here, k-stable space. So any space is the k-stable if for the any continuous map onto the map X to Y, we have a network of Y less than kappa whenever the I weight of the Y is less than. So such a space is called the kappa stable space, and it is also T invariant. Next is the functional perfect space. Functional perfect space is that if there is a compact space K of the CPX means you can see the topological function space with the pointwise topology, which separate the point of X, then such a space X is called the separate of functional perfect space. And the functional perfect space is also T invariant. So this is another property. A functional perfect compact space is also called the Hilbertian compact space. And the Hilbertian compact space is also a T invariant, a T equivalent, or T invariant properties. Next is a sigma compact space. So any topological space is said to be the sigma compact if it is a union of countable many compact subspaces. And it is also T invariant properties. If X is a compact space and both are T equivalent, then Y will be also T equivalent. Next is the Lindelof sigma space. So any space is the Lindelof sigma space if X has a cover U such that all the elements of U are compact, and there exists a countable family F, which is a network with respect to the U. And it is also T invariant properties. Now here we have two important unsolved problem that is related to the pseudo compact space. So what is the pseudo compact space? A space is simple called the pseudo compact if continuous image is bounded. And the first problem is here that if X is a T equivalent to Y and Y is a pseudo compact, then X must have a pseudo compact or not. So here it is not we can directly say that how it is possible. Here I am working on this problem, and it takes time that how to work on this equivalency. Either it is under the certain conditions, or with this same question here we can solve. Same here. The second problem is that if X and Y are the T equivalent, and if X is a sigma bounded, then how the Y is sigma bounded. So here it is just my assumptions that how to solve this problem with the help of that given problem, given result as we discussed earlier. So this two unsolved problem is raised in the 1989, and somebody work on this, but not it is completely solved. So we are working on this. So finally here we here discussed some important in T invariancy. One thing is also that here we consider only the weakest topology on the CX, that is a topology of pointwise convergence. Now the same problem here we can generalize that if you are going to consider the finer topology, Finite topology means either we are going to consider the topology of compact convergence or the fine topology or some other recently topology introduced, then how this t-invariancy behave. So the main question is here that under the weakest topology, the t-invariancy behave very well. But what is the next step that we are going to discuss about the higher topology on the set of function space? And we can also generalize, because here this result is only for the Cx. Cx means the set of real valued continuous function. But we can also replace by this Cxy, where we can consider the not only R as equality in a space with a standard topology, that we can consider any very general topology on the Y, that is the Cxy. So there is a lots of opportunity for finding the general result from this base result that we will work in the future. So it is in from my side. So if anybody have a question, you can ask.
Let's go ahead and thank our speaker really quickly here. Thank you so much for the great talk. We might have time for like one quick question.
Yeah.
When he has one. Please unmute yourself or put it in the chat. I guess in that case, let's thank our speaker again.